Okay, tonight I'd like to go through with you guys speed of light problems. I'm going to give you a few days to work on these problems, not that they're really hard, but I know some of you have AP tests, so I figure this way you could get your work done for this class when you have time and study for your AP test when you need to. This will be due on Wednesday night at 11:59, so make sure you get it in before Wednesday. And then Thursday we'll move on to our next lesson. Okay, speed of light problems. I want to remind you of some of the key ideas from the other day. One is when lightning hits, sound and light emanate outward. Sound travels relatively slow. Light travels really fast, but not instantly. When that lightning strike happens and a person on this lake sees it, it took time. It might only be milliseconds or microseconds, but it did take time for the light to travel to where they are. And you can see the sound going very slow. The light traveled outward in the same manner, just quicker. Remember that light does not just mean stuff you could see. It's all of these things. So we'll have problems dealing with radio waves, or maybe ultraviolet rays or X-rays. They're all light. They all travel in a similar manner. Okay? Remember your index of refraction. Higher numbers means light travels slower. So just like sound, the speed is determined by what it's traveling through. So you take the speed of light in outer space, which is 3 e to the 8th meters per second. 300 million meters per second, fastest speed out there, and then you divide by the index of refraction. So if the light was traveling through glycerin, you would take 300 million and you would divide by 1.47, and that would be the speed of light through that material. I also want to remind you that when you see things that are very far away, it takes a lot of time for the light to come to where you are so that you can see them. So with the Andromeda galaxy, I was telling you guys, it takes light 2.5 million years to get to the Earth from the Andromeda galaxy. Sometimes they'll refer to these as light years. Light years is actually a distance. It's the distance light travels in a year. So this galaxy would be 2.5 million light years away. It means it took 2.5 million years for light to travel. That's an easier way of saying it than these number of meters, because these numbers get so big that it's hard to put any relevance to them. So for really big distances, they're sometimes given in light years. Okay, so for each problem, just like with the speed of sound problems, you're going to show me a picture of your work. And just like with the sound problems, I'm going to be grading you on the quality of your work. Make sure you show me the equation, the numbers you plug in, the answer, the unit, and any drawing that you might need to do to help you visualize it. Some of these you won't need to do that, and I will state explicitly when you do and don't need to show your work. So the first problem, you don't need to show your work. I just want you to fill in the index of refractions from the table that we had in your reference packet or on this video, and then show me that you can find the speed of light based on that index of refraction. Simple problem. You don't have to show your work. I just want to make sure it was clear what I was telling you about how to get the speed of light in these different materials. The next problem you're going to deal with will be a fiber optic cable. Fiber optic cables is how many of you get your TV and internet. The signals are sent as light waves through a fiber optic cable. It's more efficient than sending electricity through a copper cable. And I'd like you to figure out how much time it takes light to travel through a cable. So I will give you the index of refraction. Use that to get the speed. I will give you the distance it's traveling from the broadcast spot to your house. It's going to be in kilometers. Make sure you put it into meters. And figure out how much time it takes to reach your house. It should be less than a second. I don't want it in seconds. I want you to use a metric prefix. Nanoseconds, microseconds, milliseconds, whatever seems to be the most appropriate. How much time does it take? Okay, then I'd like you to do one with the Curiosity rover. And right now there is a rover on the planet Mars that is exploring the surface. And it sends signals back to Earth. And I want you to figure out how much time it takes the signal to go from Mars to the Earth. We're having Mars and the Earth on different sides of the sun. So when you do this, you're going to have to figure out the total distance by combining the distance from the Earth to the sun and the distance from Mars to the sun. Okay? This answer is going to be way bigger than a second. So don't give me your answer in seconds, but convert it to minutes or hours or days or years, whatever is most appropriate. Then we have one of the most beautiful things humans have ever seen. This picture that you see here is a real picture. It is a thing known as the Bubble Nebula. This picture was taken a few years ago by the Hubble Space Telescope in 2016. And this object, it turns out, is 8,000 light years away, which means that what we're seeing when we look at this Bubble Nebula is we're seeing how it looked back in around 6,000 BC. 6,000 years BC is what you're seeing right here when you look at that. It no longer looks like this. We won't know for another 8,000 years how it looks today. Okay? So I'd like you to figure out how many meters away it is and expect a really big number. You do not need to put it as a metric prefix. You can simply express it in scientific or e-notation. This next one's a little tricky. We got the Channel 6 news van that has a satellite dish on it. When they're filming something, they would take that signal. They would send it as a radio wave up to the satellite. The satellite may then reflect it down or broadcast it down to the actual TV studio. I don't care about the second part. You're going to figure out how long it takes the signal to go from the truck to the satellite. I will give you the horizontal distance and I give you the vertical distance. Use that to get the actual distance and use that to get the actual time. Again, it should be less than a second, so use a metric prefix to properly express it. We talked about a light year. I now want you to talk about a light nanosecond. Figure out how far light travels in 1 nanosecond. And we'll use that to describe how large an object is. So I'd like you to say, how far is a light nanosecond? And then how many light nanoseconds tall are you? So if you're like 6 feet tall, how many nanoseconds would it take light to travel that distance? Obviously, I'm not 6 feet tall. Okay, the final one, we're going to harken back to the speed of sound that we talked about before, and I want you to use the speed of sound to kind of figure out something about the speed of light. So you're out playing soccer. It's 25 degrees Celsius, which is about the high temperature today. This is Sunday. You see a lightning strike. You time it until you hear the thunder. It's 3.2 seconds later. I want to know how much time it did take for the light to reach you. So what you're going to do is start with sound. And you're going to do just like you did the other day, and you guys did beautifully with this. Find the speed of sound at 25 degrees. Look at the time it took the sound to reach it, and figure out how far away was the lightning strike. Then do light. You're going to do the velocity of light, distance over time, whatever distance you calculate here, put it in here, and solve for time. Again, it's going to be really quick. Put it with a metric prefix. For all of these problems, except for the fiber optic one, you're going to assume that light travels at 3 e to the 8th. Do not worry that it's traveling through air. Air and space have almost the exact same speed of light. Anyway, guys, I hope you do well on your AP test if you have them. If not, you can take this work kind of slow. Just make sure you get it into me by Wednesday.